overview about the cost. So like in my presentation, I'm going to show you like an assessment of like different hydrogen supply chains, and we do like a techno-economic assessment. So we are going to see, okay, what is the overall, a little bit of the way because I would like to move on a little bit. However, so first of all, the outline of my presentation. So, okay, we will start with the background, but just like a very short background because we already had some lectures during this week, and I guess you already know what green hydrogen is. So second one, there we're going to define the different hydrogen supply chains we're going to examine. You've heard that you can use, for example, ammonia, you can use LHCs, you can use liquid hydrogen or methanol. So there we will define like the specific hydrogen supply chains and the case study we're going to do. Now afterwards, yeah, since I'm from a university, of course the methodology and the data we use needs to be shown, just for you also to understand, okay, how did we do this kind of assessment and how do we get to these kind of final values, because yeah, that's all what research is about, it, that there's big transparency and you can understand, okay, what is the background of these kind of numbers. And then the fourth part, these are the results, probably the most interesting part of this presentation. And there you can see like the different cost relation of like conversion processes and deconversion processes of transportation costs and so on. So like this is probably yeah, the most interesting part. And in the end, because you will see like a lot of numbers, you will see like a lot of shares, I will just give like final conclusions to the different areas, so you can get like a take-home message and get like the most important points of the different areas. Okay, now you're familiar with the outline, and let's just get started with the background. And yeah, just very shortly here, you can see like in the future we expect like a significant growth of the hydrogen demand, like in a lot of different sectors. And yeah, but I will skip this kind of slide and we go directly to this kind of picture. And you can see here, this kind of figure shows the hydrogen production costs for the different regions. Red means we have like very low cost, and blue means we have like very high cost. And you can see like here in the Northern African region and the Middle East, and also like in Central Africa, the hydrogen production costs, they are partly significantly lower than, for example, here in Central Europe or even in Spain or Germany. We can see that our hydrogen production costs are high. And of course, when the production costs are higher, it means also like the end, the person who wants to have hydrogen, he needs to pay more. And therefore, it can be interesting to produce hydrogen not where you need it, but to produce hydrogen in a region where the costs of hydrogen productions are low, and then ship it or transport it by pipeline to Europe, or in this case to Germany. And another important fact is that, like, for example, if we take a closer look on Western Europe, there it's like a very dense area. Like, we don't have a lot of space there left. And therefore, we don't have like a lot of space to install like the wind power plants or the photovoltaic power plants. However, like in the region here, we will consider also in our study, we can see that there's like a lot of unused land. So for example, there's desert, and it's more easy to install, to use these kind of surfaces to install photovoltaic and wind power and so on. So it's not only like that we have like higher solar radiation, but also we have like better land availability. And these kind of two facts, they make it likely that in the future we're going to need like hydrogen transportation over longer distances, because nowadays, we've seen it on the slide before, we're already using a lot of gray hydrogen, but there most of the time we transport the natural gas. And in the future, we're going to need to transport the hydrogen itself. And yeah, this is just like the statement I gave. And so this was the background. And now I would like to talk with you about like the different hydrogen carriers we will consider in the case study. And before, we need to make the outline of the different countries we will consider. And it's always like a very complex topic. So here we try to break it down like more to an easier message. First of all, we have here Germany, where we want to have like the hydrogen. And second, we consider here the Oman for like a hydrogen production region, because like Oman is often considered as a country which could potentially export green hydrogen in the future. And then we have like the different locations. Here it's Raisut, this is like a big harbor in Oman, and we want to deliver the hydrogen to Wilhelmshaven. Wilhelmshaven is like a very important port to Germany, and several, like one company already announced that they want to build up like their hydrogen at home. So it's like likely that the big parts of energy imports in the future will be over Wilhelmshaven, probably also in Hamburg harbor. And here we just consider the transportation per ship. So we exclude the pipeline transportation. I can tell you, like from our previous research, if we consider pipeline transportation, in most of the cases, pipeline transportation of gaseous hydrogen is the lowest cost option to transport hydrogen and also to supply hydrogen. However, here we have like longer distances, so it can be also economically viable to use the shipping. Furthermore, like the big advantage of shipping is you have flexibility. Like with a pipeline, let's say we're building a pipeline from Morocco to Europe to Germany, you always are bound to this kind of pipeline. And if there are like political issues, this can be very dangerous, or can be very complicated, as we learned like since last year. So therefore, like hydrogen export or import via ships gives us more flexibility. And therefore, maybe also like from a political perspective, it's more desirable. Okay, but I don't want to get lost in this kind of topic. So now we know like we want to transport green hydrogen from Oman to Germany, and now we need to discuss like which kind of conditioned hydrogen options we're going to consider. You can see here like gaseous hydrogen under standard temperature and pressure conditions has a super low volumetric energy density. So it's not, we cannot use this kind of like standard temperature and pressure conditioned hydrogen for transportation because it's not economically viable. Otherwise, we would like need like a lot of volume to transport like just a little fraction of hydrogen. So we can compress it, and we can see here like with 350 bars, the volumetric energy density increases. But you will see later it will not increase a lot compared to the other options. However, we need also for this kind of compression some electricity, but not so much electricity than for the other parts. But still, because of this kind of low energy density, it seems to be not feasible for longer distance shipping because the energy density is still too low. And now we can take a closer look, for example, on liquid hydrogen. Here we can see that if we have liquid hydrogen, which needs to be liquefied, and then we need temperatures of minus 253 degrees, then we can see that the volumetric energy density is more than 2 times higher than for the compressed gaseous hydrogen at 350 bars. So this is now like an energy density where it becomes interesting to ship hydrogen over the sea. But we need like more electricity to liquefy the hydrogen because we all know like minus 252 degrees, it's very, very cold. So we need to put like a lot of effort into it to liquefy it. And the next option, these are the LOHCs, which we just saw before. And we can see like here in this kind of case, I think it's CO2 low, what I considered. And yeah, we can see here also we have like a significantly higher energy density, volumetric energy density than for gaseous hydrogen, and we can transport it as we heard like in the given mineral oil infrastructure. However, yeah, we have just talked about it. We need like heat for the dehydrogenation, and we need to have like this kind of carrier material, which has like maybe also like a significant cost contribution. Next one is the methanol. Methanol, sometimes it's also classified as a liquid organic hydrogen carrier because it's also an organic component. However, most of the concept for methanol consider that the CO2, what we're going to need to produce the methanol, and in the end, what we will get again when we crack the methanol, will be released in the atmosphere again. So we don't have like the retransportation of our carrier material to the production site. However, recently they're also popping out some concept where we have like this closed carbon loop. Now for methanol it's very important, if we're going to release the CO2 into the atmosphere, it needs to be green. CO2. Otherwise, we will have like a very significant global warming potential, and we don't want this. We want to supply green energies. And also for methanol, we can see here the volumetric energy density of the hydrogen, which is bound in the methanol, is very, very high. So far the highest, and it can also be easily shipped in the given infrastructure because we already do it nowadays. And also for methanol, very important, we need heat to crack the methanol into hydrogen and oxygen again, and it's the same as for the HCs. Now, last but not least is ammonia. We can see here ammonia under standard temperature and pressure conditions is gaseous, and therefore also the volumetric energy density is very low. However, we can liquefy it, we need like temperatures of minus 35 degrees, and then it's already liquid, so we don't need so much energy then for the liquid hydrogen. And we can see here we have like very high volumetric energy density, means we can transport like in the liquid like a lot of hydrogen without needing like a lot of alumina. Okay, so far so good. So we, in our assessment of the hydrogen transportation from Oman to Germany, we consider now these 4 carriers. It's liquid hydrogen, it's like LOHC, in this case benzene-toluol, or toluene in English. It's ammonia, and it's methanol. And we always have the same frame conditions. So we start with compressed gaseous hydrogen at a pressure level of 100 bar in Oman, in the red suit. And we're coming out again with compressed gaseous hydrogen in Germany, in Wilhelmshaven, because it's more or less likely in the future, if we're going to have like a pure hydrogen demand in Germany, that we're going to need like a hydrogen pipeline network. And since the pipeline network is the lowest cost option to transport hydrogen or to distribute hydrogen in Germany, we consider like this as the frame condition for Germany. So we have like compressed gaseous hydrogen in Oman, and we want to have again compressed gaseous hydrogen